This is about pendulums. Pendulums are very important in the history of science as a way of measuring time accurately before we had better ways of doing it, and also as a way of looking at oscillations. What we're going to look at is what factors affect the period of a pendulum and how we calculate the frequency of a pendulum from its period. Okay, so first of all, here's a nice simple pendulum. We've got a fixed point, we've got a string or a rod which has got very little mass, and then we've got a big mass on the bottom. This pendulum's got a period of 1 second. That means it takes 1 second to go left and back to the right again, there and back, there and back. That's one oscillation. If it has a period of 1 second, that means that you get one oscillation per second. That's a frequency of 1 hertz. Things we could change about this: well, we could change the mass at the bottom, we could change the amplitude, how far it's swinging to each side, which we might measure as a distance or an angle, and we can change the length of the pendulum. So we've got a nice simple thing here where we've got 3 possible variables, and we might want to think about the effect of increasing each of those 3 variables on the period of the pendulum. Got a nice little animation to help us out with this. So here's our little pendulum. We can pull it back to an angle, let's say 10 degrees, we'll let it go. So it'll swing forwards and backwards. Down here we've got a little timer, and the timer is going to time one oscillation. It actually does it from the middle there and back to the middle, 1.42 seconds. I can then put on a second pendulum, and we can change this pendulum so that I can make it the same. First of all, let's have a look at mass first. So if I make this second pendulum 5 times the mass of this first one, that should make it pretty obvious if there's a difference. Whoops, got the wrong one. If I pull this one back to 10 degrees, I'm just going to let it try and go with the other one. Okay, if we look at these 2 pendulums, we'll see that they swing exactly together. So in fact the mass hasn't made any difference at all to the period. I can just check that with a timer. If I time in now the red one, pendulum 2, still 1.42 seconds. So mass actually has no effect on the period of a pendulum. That might seem surprising, but if you think about falling objects, there's more mass, which means there's more force pulling it back towards the middle, but it's also harder to accelerate. That's the same principle as when you just drop 2 objects. Heavier objects don't fall faster as long as we can ignore air resistance. So if we put the 2 pendulums so they're the same mass, up to the second pendulum, and I have a look at the effect of the amplitude, you might think again that making the amplitude bigger would make the period be a lot longer, but if I try and let these 2 go together, what you'll see is they still swing pretty much together. However, if we time it, you'll notice that the time has increased just slightly to nearly 1.43. If I pull it a little bit further to 30 degrees, okay, you'll notice that the blue one is just getting slightly ahead of the red one. If I do it on the timer, you'll see it's now 1.44 seconds. So it does make a little bit of difference, but only a very small difference. This is because although the red one's got further to go, it also moves a lot faster. These 2 effects almost cancel each other out. So for small angles, the period doesn't depend on the angle. So the third thing we can do is to make the second pendulum longer. Let's make it twice as long. Okay, you can see probably already that it's going slower. I can't catch it. Missed it again and again. There we go. So if I swing these 2 pendulums both at the same angle, okay, you'll notice clearly the blue one is going much faster. If I start the watch on the second one, you'll see it's now taking over 2 seconds. In fact, if I make it 4 times as long, so if I make it 2 meters long, now you'll find it actually does exactly 1 oscillation for every 2 that the blue pendulum does. If we start the time, you'll see that the time is now 2.84 seconds, twice as long. Okay, so if I make the pendulum 4 times as long, the period is twice as long. Okay, if you want to have a look at PHET, that's the University of Colorado site, you can actually have a little play with that if you want to. Okay, so here's our pendulum, and again, if we did those experiments and we plotted all the things, this would be our graphs. So change in mass, it doesn't have any effect, it's a bit of a funny graph, but you'll notice it's perfectly horizontal, there is no effect at all of changing the mass. If we increase the amplitude, you'll notice that it's pretty much constant for small amplitudes. As we start to get bigger, it starts to just increase a little bit. And if we increase the length, okay, then it definitely does make a big difference. So longer pendulums do take longer to swing. Okay, last part of this is to relate the period to the frequency. If you understand those two terms, it shouldn't be too hard. So we need to get our definitions right. The period is the time for one complete oscillation. Be careful here, that's there and back, that's one oscillation. And the frequency is the number of oscillations that we get in 1 second. So what that means is if the period was half a second, then the number of oscillations we'd get in a second, the frequency would be 2 Hertz. If the period was a tenth of a second, we'd get 10 oscillations per second, 10 Hertz. How can we put this into an equation? Well, the period is 1 over the frequency. That's written on your datasheet as T equals 1 over F. If you rearrange that, you also get F equals 1 over T. They're just the inverse of each other. Okay, quick example. So pendulum completes 45 oscillations in 1 minute. What's its frequency? Notice a little catch with the unit here. This is minutes. So the first thing we do is to work out the period, which is the time divided by the number of oscillations. So it takes 60 seconds to complete 45 oscillations. That's 1.33 seconds for each oscillation. Okay, little check for you mentally just to see if you've made a silly mistake here. The period is more than 1 second. You've only got 45 oscillations in 60 seconds. Each one must be taken more than 1 second. If we want to work out the frequency, that's 1 over the period. That's 1 over 1.33. That comes to 0.75 Hertz. Again, little check, it's less than 1 Hertz because there's less than 1 oscillation every second.